Okay, Maddie, I'm going to try to do this so that you can see me and see my screen at the same time. So here we go. So for the volume problems, you have to think more of 3D, right? Because you're going to revolve it or rotate it around a certain axis of symmetry. So you're going to have this three-dimensional object. So when I would teach this, I would also ask the students to do a few things before we actually set up the problem. The first thing is we want to figure out where our axis of symmetry is. If our axis of symmetry is the y-axis, or is our axis of symmetry the x-axis, we really want to figure out where that is. The second thing we want to do is figure out where our rectangles are. We need to figure out the shaded area, the area that we're talking about, and then figure out if our rectangles are going to be stacked along the x. Are we integrating with respect to x? Or are our rectangles going to be stacked with respect to y? We're going to be integrating with respect to y. If your axis of symmetry is like this, and your rectangles are stacked along the y and they're perpendicular, the axis of symmetry and your rectangles are perpendicular, then you're going to use the disc or washer method. If your axis of symmetry, let's say, is the x-axis, and you're stacking the rectangles along the x, you're integrating with respect to x, they're perpendicular, so then you're going to still, again, use the disc or washer method. So anytime your axis of symmetry and your rectangles are perpendicular, you're using disc or washer. You're going to do pi r squared. You're going to do a whole bunch of different areas of these circles, it's going to be, as you rotate these rectangles around. So you're either going to do pi big R squared if there is not going to be a hole as you rotate it around, and if there's no hole, the rectangles, when you rotate it around that axis of symmetry, have no gap, then you're going to do pi big R squared. Right? If there is a hole, though, then what you have to do is think of a washer. Think of a circle with a hole in it. You've got to find the area of the whole thing, but then subtract out the area of that small hole, right? So you've got to do pi big R squared minus pi little r squared, or bring the pi out as a GCF and do big R squared minus little r squared. That's, again, if the axis of symmetry and the rectangles are perpendicular. Now, let's say your axis of symmetry is the y-axis, but your rectangles are stacked along the x. If your axis of symmetry is here and your rectangles are here and you start to rotate, well, then you've got a shell method. So anytime your axis of symmetry and your rectangles are parallel, then you're going to use the shell method, which is integrating from a to b of 2 pi ph. I don't know if that's always the same letters. It might be different for different textbooks, but I always used 2 pi ph, where p was the distance from the axis of symmetry to any of those rectangles. However you were stacking them, it was the distance from your axis of symmetry over to any one of the rectangles. The h is the height of all those different rectangles. So if your rectangles are in between two curves, we've got to figure out the height in between those two curves and do top minus bottom. If it is just the height of the curve, then we just use the function f of x as the height. So again, if the axis of revolution and our axis of symmetry and your rectangles are parallel, then you're going to do the shell method. Perpendicular, you're going to do disc or washer. Parallel, you're going to do shell. Okay, so let's look at a few of those. So this was number 1, 2, 3 is the first one that we're going to do when we talk about volume. So it looks like we're have a couple different, we have a function x squared plus 1. We have the line x equals 1, x equals 3, and the x-axis, and we're rotating it around the y-axis. So you drew a graph of your parabola, the x squared plus 1. I have my lines here, x equals 1 and x equals 3, so you can see my little shaded part. Now my axis of rotation, where I'm rotating around, is the y-axis, right? So if I imagine that this is my axis of symmetry, and I know that I want to start at 1 and end at 3, my rectangles are going to be along the x, right? We're going to integrate with respect to x. If my axis of symmetry, though, is my y-axis and my rectangles are stacked like this, you notice that the axis of revolution and the rectangles are parallel. Since I know they're parallel, that's how I know I'm going to use the shell method. I'm going to do my 2 pi ph. My rectangles are stacked along the x, so I know I'm going to integrate it with respect to x. I know that I'm going to start at x equals 1. I'm going to end at x equals 3. So now I just have to figure out my p and my h. So I'm integrating from 1 to 3. I have my 2 pi outside. My p, remember, is the distance from the axis of revolution to any one of the rectangles. So if the y-axis is my axis of revolution, if I go to the first rectangle, or the second rectangle, or the third rectangle, or the fourth rectangle, any rectangle that I hit, how wide is that distance? How far is that distance from the axis of revolution to any one of those rectangles? Well, if you look, it's whatever distance I am away on x. If x is 1, if x is 2, if x is 3, whatever x is will tell me my distance from the y-axis over to any one of those rectangles. So my p is x. The height is the height of all these different rectangles. Now, my rectangles are different heights depending on where they're at. This rectangle is a little bit smaller than the next rectangle, then it gets a little bit bigger, but it's all based on that function, right? And so the height of any of those rectangles is based on the function. So my height is going to be my function x squared plus 1. So I have my x is my p, the distance from the axis of revolution to any of the rectangles, and the height of all those rectangles is my x squared plus 1 function. So that you can distribute, you can integrate from there, and then hopefully find the volume of that revolution using the shell method. If you look at number 4, we have the square root of x, which you've kind of drawn. We have x equals 1, this line. We have x equals 4, this line. So that gives me a really good starting point and ending point. So I can imagine that my little rectangles are going to be kind of stacked from x equals 1 to x equals 4 along the x, right? But on this one, it says that my axis of revolution is the x-axis. So if that's the case, and I imagine that this is my axis of revolution, but these are my rectangles. My axis of revolution here, but my rectangles are here. It looks like those two things are perpendicular, right? And since they're perpendicular, I'm either going to use disk or washer. If I'm taking these rectangles and I'm rotating it around the x-axis, I don't see any gap in there where I'm going to have a hole. And so as I'm rotating these around, it's just going to be a solid disk. So I'm going to use the disk method, and I'm going to do pi big R squared. Okay? My big R is my radius. My radius of any of those disks from the axis of revolution up to the top. So from the axis of revolution up, from the axis of revolution up. So as I rotate those, that'll be my radius of those little disks. The radius then looks like it's going to correspond with my function. It's going to change as my function changes. So the radius is going to be from the axis of revolution all the way to the very top, my function. So I'm going to integrate it from 1 to 4. And I'm going to do pi big R squared. My big R was my function, my square root of x. Don't forget to square it. And then we're integrating it with respect to x because my rectangles are stacked along the x. When I square a square root, that goes away. And so my integral turns out to be pi times the integral of 1 to 4 of just x. And then you can integrate and evaluate from there. Let's look at number 5. Number 5 has an 2x squared, so a parabola, a y equals 5, and so it looks like it's that shaded little bowl, right? And it says I want to rotate it around the y equals 5, so I want to rotate it up this way. Now my axis of revolution then is this line right here, and it looks like I have a good starting point and a good ending point. That's where the shaded area is. But it looks like the starting and the ending is along the x, right? It's whatever this x value is and whatever this x value is. So it looks like I want to integrate with respect to x. That means my rectangles are going to be stacked like this, right? And so if my rectangles are stacked like this, but my axis of revolution is the y equals 5, it looks like those two things are perpendicular. My axis of revolution, my rectangles are this way. Since they're perpendicular, I know that I'm going to use either disk or washer. If I imagine taking these rectangles and rotating them around that y equals 5, it looks like those rectangles are right next to it, right? There's not going to be any gap when I go and rotate this around. It looks like if I were to imagine a 3D rotation, it's going to kind of look like a football shape, right? And there's going to be no hole in that football. So I know I'm going to use disc instead of washer. I'm going to rotate it around. I'm going to stack my rectangles along the x, so I know I'm going to integrate it with respect to x. I'm going to do pi big R squared. Now, the problem is we need our limits of integration. We need to figure out where to start and where to end. Remember, we had to figure out where to start and where to end by looking at these 2 points right here. It looks like those 2 points are actually where your parabola and that y equals 5 line intersect. So we can find the intersection of any 2 functions by setting them equal to each other. So that's what it looks like you did on your paper. You set the 2 equations equal to each other so you could find out where those 2 intersections are, really where you start and where you end. Your limits of integration are positive square root of 5 over 2 and negative square root of 5 over 2. So that's my A and my B. And now I need my big R, my radius. Remember, your radius is how long or wide or big all of your little rectangles are, right? So it looks like it changes, again, as you follow that curve. Now, because you're actually finding the distance in between those 2 curves, it's really a top minus bottom. Because your rectangles aren't always 5, but they're not necessarily underneath. What color can I use? Green here. They're not under your function like this, so I wouldn't want to use my 2x squared as my rectangles because that would be the length underneath. I want the distance in between the 5 and that parabola. So to find that, you're going to do your top minus your bottom, kind of like the area, right? Top minus bottom. That top is always going to be that y equals 5 line, 5, and then your bottom is going to correspond to your function. So top minus bottom here, your big R, your radius of all those discs, would be 5 minus 2x squared. Don't forget to take that whole thing and square it because you're doing pi R squared. Okay, hopefully you can FOIL it, integrate it from there. I probably wouldn't do a U substitution. I would just FOIL and then integrate and evaluate from there. So that was what, 3, 4, and 5. Let's do one more here, number 6. Number 6 has 2 different parabolas. If you look at the first one, the 6 minus x squared, if you were to rewrite that in a different order, would be a parabola that opens upside down. The other one is an x squared minus 6x, so that's a parabola that opens up. You could even graph it in your calculator to kind of see, but it kind of looks like the picture that I've drawn. So you can see that there's a little bit of an area in between those 2 parabolas that kind of look like this. We want to take that and we want to rotate that around the y-axis. So now we want to take that and rotate it, okay? So I can clearly see that there's 2 points of intersection, and it looks like those are really good starting points and ending points of that little shaded area. But it looks like those are along the x. And so when I go to stack my rectangles from start to end, it looks like I'm stacking them along the x-axis. From that starting point to the ending point of my shaded region, looks like it's along the x-axis, right? So I know I'm going to integrate it with respect to x. But now where's your axis of revolution? Well, your rectangles are here, and didn't it say that we want to rotate it around the y-axis? So if this is my axis of revolution and these are my rectangles, it looks like those are parallel. And if they're parallel and I rotate it around, I'm going to use the shell method. So I know then that I'm going to do my 2 pi ph, and I'm going to do it with respect to x. So I need a starting point and an ending point on my x. It looks like those are the 2 intersection points. So I need to set my 2 equations equal to each other. Set them equal, move everything to the same side, and factor, and it looks like they intersect at 0 and 6. So those are my limits of integration. So when I have my limits of integration, I know that I'm stacking them along the x. I know that the axis of revolution is parallel to it, and so I know I'm using the shell method. So I've got to do my 2 pi ph. I've got to figure out p. Remember, P is the distance from my axis of revolution to any of those rectangles. Remember, my axis of revolution is the y-axis, so from here to